Hi guys, Dr. J here, and in this video we're jumping into interferometric SAR, or InSAR. We'll talk about the theory of InSAR and some basic applications. So we've talked in other videos about amplitude, we talked about backscatter. How about the phase? So we've talked about what phase is, but how do we use the phase to do imaging? So phase is a function of distance from the satellite to the ground. Again, it's this horizontal distance, horizontal meaning along the same direction as the ray. So in this case, it's not actually horizontal. But it's along the same path as the ray is traveling. And you can kind of see here, at some point the ray stops because it hits the ground. And the point at which the ray stops is the phase of that wave. Now for a satellite like ERS-1, this is one of the older InSAR satellites, not up anymore, has a 6 centimeter wavelength. It's 780 kilometers above the surface of the ground where it's orbiting. And so there are many, almost probably 1 million wavelengths between the satellite and the ground. So we can't really determine what that number is because we don't know precisely the distance of the satellite to the ground. We don't know exactly the phase. But what we can do is look at the relative phase, which is basically just the phase of this last wavelength. So we have 2 passes of the satellite. We need 2 passes for interferometry, right? We need 2 signals. So we're going to do pass 1, pass 2. We'll be able to measure the difference in the phase. So if there is, let's say there's an earthquake on a fault in between those 2 passes. So again, just to be clear, we're imaging all the time. For Sentinel-1, we're imaging every 12 days. For ERS, it was about every month. For ALOS-2, it's about every month. InSAR, the upcoming mission next year, will be every 12 days. So we're imaging on a regular basis the same location. Here we've imaged one time and nothing has happened, but then in between this first acquisition and the next acquisition, any time in between there, you have an earthquake. And it could be the second after the acquisition is made, it could be the second before the next acquisition is made, or it could be any time in between. Any time in that time period, you're going to see, or if something happens anytime during that time period, then you'll see the same exact signal on the image. You'll see this change in phase, this change in the total length, compared to the first time. So just imagine you take this image, or this wave, you take this wave and you subtract this wave, you'll get this difference here. This difference is the little red portion. And we can make a map of that because we can do this difference for every pixel in our image. So phase shift varies with distance from the fault. That's because there might be different amounts of deformation depending on how close you are to the fault. Here we are, we've taken 2 images. We're going to take the phase from each image, and I mentioned in another video that the phase looks random. It looks like white TV noise, old static TVs from long ago, or old static noise from old TVs from long ago. This is kind of what this looks like. So it's spatially uncorrelated. The interferometric phase is spatially uncorrelated, random. But it's temporally correlated so that if you take the phase from 2 different images, the phase, and so just imagine, remember the phase of a pixel is a coherent sum of all the scatterers in that pixel. So let's say you have a car and a tree inside of a pixel, you'll get the sum of those 2 scatterers, and that's not going to change too much, even if the earthquake happens and the whole scene moves down or moves up a little bit, moves a little bit because of the earthquake. The overall scattering is not going to change too much, and so you have temporal correlation. If I pick a particular random pixel from this image and the same pixel in the second image, the scattering properties are likely to be very similar. And the only difference will be this deformation which has happened. So then we take the difference and we get an interferogram. This is an interferogram, and this is showing you how much, I have to be a little bit careful here because there are noise sources in this as well. But basically, this is in the simplest world, this is a measure of how much deformation has happened in between the time of the first acquisition and the second. So we've got our 2 acquisitions, and now we have a measure of the phase. Now let's look at this phase in more detail here. So we have our first SAR acquisition. That's a complex image. We take the phase from both images, we difference the phase, and we have our image. Now what do you see? One of the things that you should notice right off the bat in this interferogram is that you see repeating colors. So you go from yellow to red to maybe purple and blue, and then it repeats. Yellow, red, and then purple and blue. I may have the colors wrong. I'm a little bit colorblind. I apologize if the colors aren't quite right. But you see the colors repeat. They repeat in cycles. And this is because this is a measure of phase. And we don't know the absolute phase, but we can get the relative phase. And so what we do is we wrap the phase from 0 to 2 pi. So the deformation that you see here is only between 0 to 2 pi. And what happens if your deformation is more than 2 pi? And what is the 2 pi? It's 2 pi radians. So 2 pi radians is going to be a full wavelength. So one full wavelength for every 2 pi radians of phase that cycles, you have one wavelength worth of deformation. So for Sentinel-1, C-band, about 4.5 or 5.5 centimeters. Every color cycle that you see in the image is going to be about 5 or 6 centimeters of deformation, depending on what that wavelength is exactly. For L-band, if we're using ALOS or the upcoming InSAR mission, that is 22 to 25 centimeters wavelength. So every time you see a color cycle, that's going to be 22 to 25 centimeters of displacements, again, depending on the specific wavelength of that sensor. So here we see yellow in the middle of this bullseye pattern. Yellow, 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 yellow. So that's 1, 2, 3, 4. 4 color cycles. So what we would have to do to get the total deformation is to say, okay, we have 4 color cycles, and our wavelength, I don't remember what the wavelength is for this sensor. Let's say it's 5.5 centimeters, or let's say 5 centimeters. We have 4 color cycles. That's 20 centimeters of deformation in the center of this bullseye. And it reduces as you go out. So here, maybe this is the reference. And it's important to note that all interferograms have a reference. There's some point in the interferogram, which is essentially the 0 point, and then all this deformation is relative to that. So let's take our 0 point to be right here, and as we move this way, we start deforming, and we get up to 20 centimeters by the time we're in the center of this image. Another few things to note. One thing that you notice is something which looks a lot like that speckle noise we talked about earlier. All this kind of noisy stuff over here, this is called decorrelation. And it's where a pixel changes so much in between two acquisitions that there's no way to do this, to do the interferometry. So in other words, it looks like our original white noise images. Because phase is spatially decorrelated, now because of whatever changes in the pixels, and this happens for various reasons, whatever changes in the pixels are leading to temporal decorrelation as well. We don't have temporal correlation, and so now we can't do imagery in this area where you have all this speckle noise. What causes decorrelation? Decorrelation can be caused by vegetation growth. So if you have a lot of vegetation growing in between two acquisitions. If it's water obviously changes a lot in between. I mean, it's completely different. Has no continuity between two images, and so that's decorrelated. Snow will be decorrelated. Other things which any kind of major change to the surface. You could have a landslide. Actually, earthquakes can cause decorrelation if there's a huge amount of deformation. So you see the decorrelation over here, you see deformation here, and you see this cycling of deformation because of the phase issue. We can only go from 0 to 2 pi. All right, so let's look at another example here from Tim Wright at Leeds. So here we have our first image. We have the amplitude and phase of the image. We have our second image taken in September. First image was in August. I think this is the ERS satellite. So again, amplitude and phase of the image. We take the phase, we difference the phase, and we get an interferogram. And lo and behold, we are able to see that there was an earthquake here. Now, one thing that I haven't talked about is what all goes into this phase. So let's talk about that for just a minute. Notice that we get rid of the amplitude. We don't need the amplitude images when we're doing InSAR. We only are using the phase. So we can do SAR, and we talked about SAR in one of the other videos, with the amplitude images, but for InSAR, we're just using the phase. So what all goes into this phase change besides the earthquake or the deformation, whatever deformation is happening? There's a couple other things. Topography is one. So actually, we have to remove topography. If we didn't remove the topographic contribution to the phase, then in some cases, you would only see the topography. There would be a huge phase jump. This is going to depend on a lot of things. It depends on the perpendicular baseline, what's called the B-perp, or perpendicular baseline. This is the distance between the satellite acquisitions perpendicular to the path the satellite is traveling. So for example, a satellite travels along the path orbiting the Earth, and then the next time that goes around to that same location, it's offset from the original path a little bit. That's called a perpendicular baseline, and that leads to sensitivity, that leads to more sensitivity to the topography. If you were in exactly the same location both times, you'd have very little sensitivity to topography, and you wouldn't have to worry about it so much. Satellite position. So if there is that change in satellite position, you can also introduce kind of a long wavelength ramp, which is related to the change in satellite positions, and also whether or not you've correctly located the satellites. So you have to know exactly where the satellites are using GPS mounted on those satellites, and in some cases that's hard to do. Especially in the past, that was a little bit hard to do, so that can result in a long wavelength ramp, essentially. You've also got Earth curvature. The Earth is curved, and so that results in a phase similar to topography, and so all those things have to be removed. Many of those things are not such an issue anymore because we have really good orbits for Sentinel, InSAR, and ALOS-2, so we don't have to worry about that as much, but especially looking at older data, you really have to take that into account. And then, of course, we have the deformation. So in this case, we're looking at the 1999 Izmit earthquake in Turkey that happened in August. If there's any deformation which happens during the entire time period between those two acquisitions, you're going to see that in this one interferogram. So you may have had an earthquake. You may have had some landslides over here along the coast, perhaps, from that earthquake. You may have had small-scale faulting related to stress changes caused by the earthquake. All of those things are going to be in this one image if they happened in between the first date and the second date. So you won't be able to separate out when any of this deformation happened. If you have multiple deformations happening in one image, one InSAR image, everything which happens is just captured in that one image. So you can't separate it out in time. So here you can see lots and lots of fringes where we're cycling from, I guess we're starting at blue to green to yellow to red, blue, green, yellow, red, blue, green, yellow, red, and we keep cycling. And so what you can again do is just count up the number of fringes here to get the total amount of deformation. And we can kind of keep doing that. Here's 283 millimeters, 567 millimeters is almost the maximum. So we can look at the image this way, but a nicer way is to sort of, I'm going to use the word unwrap. Unwrap is the technical term for taking this image and converting it to an actual deformation map. But we can do it kind of, just imagine doing it graphically, by matching up how much deformation happens at each one of these color changes, and then plotting it on a graph. And if you do that for this particular earthquake, you can see this kind of deformation. So we see the south side of the fault moves to the left, the north side of the fault moves to the right. And this is, let me rephrase that, this is line of sight displacement. So we're looking at the satellite. You can see here the satellite's moving this direction, looking to the right. So the line of sight displacement, and the line of sight displacement is the displacement in the line of sight. Let me actually back up here because I neglected to mention too much about this earlier. Here's our perpendicular baseline I mentioned earlier. There's B-perp. We have our master acquisition and slave acquisition. This is older terminology. Now we use secondary and reference instead of master and slave. The first image we get of the first image of the site, when we take the second image, the deformation that we measure is along this radar wave. You can see here that the change in length here is in the same direction as the radar wave is traveling. So we call this line of sight displacement. It means it's the deformation which is happening on the ground. It's a measure of that deformation, but it's in the line of sight. So imagine for a second that you're moving exactly, that the ground is moving exactly parallel with this line. Well, then the line of sight displacement is going to be the same as the real displacement, or at least the magnitude of it is. Now imagine that you're moving exactly perpendicular to this line. Somehow you're on a hill or something, and the ground is moving exactly perpendicular to the line of sight, to the satellite. If that happens, you will see zero deformation. Okay? So your deformation that you observe is going to not just depend on the deformation itself, but also on the direction that the satellite is looking. Because if you're perpendicular to that direction, to that line of sight, that radar wavelength, or that radar wave travel direction, if you're perpendicular to that, you don't see any of that deformation. And if there's some combination of both perpendicular and parallel deformation that's happening, you're going to see only the component of deformation that's parallel. This is why having more than one look direction is so important. If we can look from this direction, and then we can also look from the other direction, maybe with another satellite, for example, then we can actually put those two pieces of information together and get more information that gets us closer to a full three-dimensional view of deformation at that site. With only a single satellite, you're only a single look direction, because remember, a satellite goes both north to south, and then also south to north. So it's actually looking, when it's ascending, it will be looking one direction. When it's descending, it'll be looking the other direction, just because of the way it's always looking to the right, and so it's going to change depending on whether it's moving north to south or south to north. The point is, with only one look direction, you're only going to be able to see one component of the deformation, and that component is the component which is parallel to the radar wave traveling direction. Anything perpendicular to that you're not going to see. You need more images to be able to get those other components of deformation. So let me go back up now to where we were. Now we're here. We see all this deformation. We calculate the total deformation. This is the deformation in the line of sight direction. So in this case, negative line of sight direction means it's negative related to the line of sight direction. And positive is positive. That means the right side of the fault the north side of the fault is moving to the right. So the positive motion there, positive getting further away, moving to the right, and the south side of the fault is moving to the left. So just like it shows here, but we have to be careful, because if this was a descending orbit, then the look direction would actually be the opposite of this. It would be traveling to the south and looking to the right, so looking to the left. And in that case, the line of sight displacement here would be flipped from what we see in this image. Okay, I know that's a little bit confusing, this whole idea of line of sight and look direction, but maybe we'll revisit that in another video just to sort of flesh that out a bit. An image of the 2008 Wells, Nevada earthquake. Beautiful interferogram. You can see a bullseye pattern here right around the earthquake. This is deformation which is happening. The other thing that you see is you see color changes, less color change, but you do see color changes in other areas. Here's this transition from blue to red. Okay, so we're changing phase here in these areas, even though there was no earthquake in those areas. And that's important to realize, is that not all the phase that you see is due to deformation. There are other sources of noise, basically, that cause phase changes between two acquisitions, which are not deformation. One big example is the atmosphere. So the Earth's atmosphere actually causes a delay in the propagation of satellite radar waves, and this delay might be different on 2 different days. And this difference in propagation delay causes a signal which is strictly related to the atmosphere. And in this case, this is mostly what you're seeing here. All this color away from the earthquake, anywhere where the earthquake is not happening, all that color change is going to be most likely related to the atmospheric effects. This is the largest contribution to the satellite signal, the InSAR signal that we observe in these images, besides the deformation itself. Each cycle of that blue to yellow to red color is, in this case, 28 millimeters of displacement. But again, it's going to depend on the satellite sensor. So if you have 5.5 centimeter wavelength, that's going to be different. If you have 22 centimeters wavelength, that's going to be different. All right, so I mentioned wrapped and unwrapped phase. Our wrapped phase is our minus pi to pi or 0 to 2 pi, doesn't matter which one, it just depends on the convention. This is our wrapped phase, and this is what our phase might look like if you have an actual phase that is just increasing. So maybe a large earthquake, a landslide, something which causes deformation over a large area. We might have a continuous deformation signal, but because we can't measure the absolute phase change, we don't know the total phase from the satellite to the ground, we're just measuring this as a function of the 2 pi, the single wavelength phase, we end up with something which looks like this. So this is a one-dimensional side view of this same type of signal. So if we were to draw a line through here, through these 3 color changes, we would see exactly this kind of a signal. Okay, And then what we need to do is unwrap this. And you can see how this works. Basically, we want to take each one of these segments and just raise it up so that the end matches up to this point. Do the same thing here, or maybe we bring this segment down, and then we end up with the unwrapped phase. So this bottom plot here shows unwrapped phase, the middle plot is the wrapped phase, and of course this is the wrapped phase that we saw before. And if we go now to an image where we have both wrapped and unwrapped, this is what it looks like. So here's our wrapped phase. You see all these color gradients related to phase changes. And then if we unwrap that, we bring all those pieces of displacement up to match so that, so that we're tail to tail. So we take this piece up so that it matches this end. We take this piece down so that it matches this end. That's the process of unwrapping. We end up with the final unwrapped image. So here we just have phase. We're just varying from 0 to 2 pi, or minus pi to pi, depending on your convention. Here now we have actual deformation. We have some negative displacements, and we have some positive displacements, up to as much as, in this case, 0.2 meters, or 20 centimeters. 20 centimeters is a lot longer than our wavelength is, in this case. So we have multiple jumps, I would say, across those displacement gradients. Once we've unwrapped this phase on the left, we get the full picture of deformation on the right. Okay, so here is just a bunch of examples now of different interferograms and what they look like. This is a compilation of multiple earthquakes from South America. You can see lots of different earthquakes in these images. Some of them are very large, have lots and lots of phase changes. Some of them are relatively small. Maybe here we have hardly any phase change at all. Here on this upper right-hand corner, we have an unwrapped phase map. So this is actually unwrapped phase for the San Francisco Bay Area. Here's just another example of an interferogram. In this particular case, this is about a 3-week interferogram. There's not really much in the way of deformation happening in this interferogram, but you still see a lot of color, and most of that is due to the atmospheric signals that were talked about. Okay, so that's the end of this part of the presentation about InSAR. So I hope you better understand InSAR a little bit better. We've talked about phase, we've talked about wrapped and unwrapped phase. Here we have examples of wrapped phase. Here we have examples of unwrapped phase, where we've taken all these gradients and shifted them so that they all match up, so that we see the continuous deformation signal. Talked about decorrelation and how if you have too much change in a scatterer between the two acquisitions, you get this decorrelation. You can't do interferometry. And we've talked about line of sight. So the deformation that we see in InSAR is just the component of deformation which is parallel to the radar traveling direction from the satellite to the ground. The only deformation that InSAR can see is the deformation that's parallel to that direction. So if we want to get 3D dimension, for example, using InSAR, we need to have multiple satellites or multiple look directions, maybe ascending, descending, in order to be able to get all that information. All right, so that's it for now, and I will see you later.